Thank you very much for that generous introduction, Alex. You see, we've been having lots of fun with Microsoft this morning. You've got a direct view of the complications. I developed this talk on my Mac, which is sitting over there. I've yet to try it on Microsoft, so this will be the first experiment to see if it works. The talk is not primarily about Spinnaker, although I will bring that in later on in the talk. What I wanted to talk to you about, again, I don't work on settling machines, so this isn't to talk about settling machines, but it's to talk about another sort of small-scale machine learning algorithm, which I suspect has a lot in common with settling machines and perhaps operates in a similar domain. So this is a novel mechanism for edge ML. And it actually emerged from the Spinnaker project that I've been leading at Manchester, as you've heard, for the last 20 years. But it kind of emerged largely through the thinking of one of my postdocs, Michael Hopkins, who has a strong background in statistical mechanics and machine learning and data modeling. And he put some ideas together, which I will bring to your notice shortly. But why do we need novel mechanisms? Well, I guess if you're in the settling machine community, you already know this kind of stuff. But current AI has made spectacular advances over the last 10, 15 years, roughly in parallel with the Spinnaker project, where we've been focusing on building machines to add to our knowledge of the brain. AI has been looking at applications, and it's made dramatic progress that I think none of us anticipated 20 years ago. But of course, it's not perfect. So what are the problems? Well, the first thing, I guess, everybody in the community of small AI, and I gave a very similar talk to this a couple of months ago to the tiny ML community, who are also in this space of looking at AI in the small. Standard AI has unsustainable energy requirements, which are growing rapidly. And the amount of energy required to train the latest artificial neural nets, which are getting bigger every day, is huge. And arguably, it's unsustainably huge. It's growing super exponentially as the models get bigger, and they do get more capable, so the results are impressive, but the energy requirements are just not going to be manageable in the future. And at the other end of the market, if you look at applications of AI, one obvious space is autonomous vehicles. And here, there's a requirement to get the energy consumption of the AI systems they require for navigation down from the current sort of 100-watt level to the 1-watt level to keep temperatures under control and power under reasonable management. And of course, legislation is applying increasing pressure to remove waste and make systems more sustainable. So one example here for the, I'm not quite sure how you pronounce LLAMA, llama, I suppose. But if that takes 21 days on 2,000 GPUs, and GPT-4 is 1,000 times bigger, then you can see that these numbers are becoming impractical. So there's the energy argument, which I guess everybody here is pretty familiar with. But that's not the only argument. Current AI is also what I would describe as brittle. So when it works, it's great. When it doesn't work, it goes wrong quite badly. And it makes errors due to noise in the data, But also a problem which I suspect we'll see more of is that it's easily fooled. In other words, somebody who wants to break the AI can do it rather easily. And that's a worry if AI is doing things like controlling your car. If people work out how to put a screen next to the road, which causes all the cars driving past to drive into the bridge, we have a problem. And I think that's going to be a growing problem. We've also, we've already heard, Richard mentioned the idea of explainable AI as one of the advantages of the settling machine. And explainable AI is of growing interest and growing importance. Again, for this reason that we need to be able to explain and justify the behavior of AI as it's allowed to take a greater role in decision making. We need to know why it made the decisions it made. So why is modern AI displaying these characteristics? There are various ways you can look at this. But one of these is if you look at the size of the parameter sets for these large-scale AI systems, where apparently GPT-4 has the order of 100 trillion parameters, then I think you can see that it's fairly clearly overfitting the data. Okay, it has spectacular characteristics, but you don't really need that many parameters to fit the kind of data that it's trying to fit. And therefore it's overfitting. And if you make small changes to, for example, an image that you're asking the system to classify, then you can break the system quite badly. Did that boing mean anything that I should worry about? No, just a random boing. So an example here is the picture on the left, which I think as humans we can look at and say with a fairly high degree of confidence that that looks like a panda. And then if you add some random noise to that, which the system will classify as a nematode. I think as humans we have trouble classifying noise as a nematode, but if we add that noise at a very low level to the image on the left, then we get the image on the right, which I think we as humans would still happily say is a panda, but according to a large neural network, it's 99.3% confident it's now a gibbon. So for some reason, that addition of noise completely fools the AI system, but I don't think it fools any of us. And so there's something going on here that means that the way AI systems are classifying, in this case, images, is not the same way that we as humans do it. Although
just those ting tong, noise. I'll just stop them.
Ting tong noise.
Yes.
How are you going to do that?
Just completely close this. Close this too. That one. That is the one that is causing trouble.
Now that's interesting. It started up in slightly different mode here, which is actually better. Now, where was I? I wasn't there. I'd got as far as that. Yes. Okay, so the systems are easily fooled. And in this case, the changes that caused the system to get the wrong classification were random errors. But of course, if you had a malign actor who was deliberately trying to confuse the system, then they could do that equally easily. And with designed noise, they could probably do it more systematically and with worse effects. So we do require systems that are much more robust than the present ones, and we do require them to be explainable, and increasingly for various important applications. This will become a legal requirement that when AI systems are taking decisions, they can explain their rationale for the decisions they come to. Another problem with current AI is that it's effectively static and inflexible. In other words, you train it once on a fixed data set, usually a very large data set, at enormous cost, and then that network is frozen while it functions. And of course, the real world isn't like that. The real world is continuously changing, and things happen both within and outside the system that require the network to adapt if it's going to perform optimally in a changing world. And so increasingly, we're seeing AI research into systems that can not only learn large data sets once and then operate with them, but they can also adapt and change as time goes on. Now, this is quite a hard problem, but of course, we do have the classic example of how you can solve this problem, and that is if we turn to biology. And if we look at biological systems, then what we see are systems that have quite different characteristics. So the characteristic of biological systems is that they can learn continuously and they can adapt to changes around them. So they're not learn once, then operate forever systems. They're adaptive systems. They're, of course, extremely energy efficient to a degree which we very much struggle to come close to with our current computing systems and technology. And when things do go wrong, they tend to degrade gracefully. In other words, performance drops off smoothly rather than falling off a cliff edge. When you add a bit of noise to the image, they will go slightly wrong rather than completely wrong. And this is a much safer characteristic and one that we'd like to see in our engineered systems. And so the work I'm going to talk about is an attempt to learn from biology and create a new type of machine learning algorithm that appears to go some way to addressing these concerns. And we called this learning algorithm BitBrain, and you probably see why as I go through a description. And I hope you find it interesting. So what's this BitBrain thing all about? And the answer is it's an innovative working mechanism, which is we call the sparse binary coincidence memory. So it has a very memory-like structure. And the name suggests how it operates. It's sparse. So not much memory is invoked at any particular time. It's binary, so things are very simple. And it's a coincidence memory. So effectively, it's a memory that stores coincidences of particular features that are identified in the input data. And these SBC memories can be built together into an infrastructure that we call BitBrain. And if you trace back where these ideas have come from, sometimes when I describe the mechanics of the memory, it won't be obvious. But the kind of ideas that are coming together in here are from sparse coding. That's the idea that you represent different concepts by very sparse digits. In the asynchronous world, we talk about N of M codes. And for a sparse N of M code, M is big and N is small, right? That's the principle. So you have 1,000 units of which 1% are active at any time. And that's the idea of sparse coding. We're putting together ideas from computational neuroscience and information theory into this. And we filed a UK patent, which is currently at PCT stage, so getting expensive. And what this memory we can demonstrate supports is single pass learning in the supervised mode, so that we can basically train it on data sets with one instance of each training sample exposed to the system. The result is accurate inference. It's not quite state-of-the-art inference, but it's close to state-of-the-art with a much lower training cost because the training is single pass. And what I'll show is that it's very robust against inputs that are corrupted by noise or other sources. And the mechanism can support continuous and adaptive learning. So it can adapt as the world around it changes. And we've demonstrated that this mechanism operates quickly and with low energy requirements and can be implemented on conventional computers in software pretty efficiently. I'll also show it can be implemented on Spinnaker, which is a neuromorphic system. It has quite neural-like properties, and it could be implemented even more efficiently on dedicated hardware if we could find the resource to put that together. The particular instances that we built so far operate either in software form on a Raspberry Pi or in the neuromorphic case, as I mentioned, on Spinnaker. Okay, and we have published a paper on this if you want to know more details. The paper is referenced at the bottom, BitBrain and sparse binary coincidence memories. So it's fairly easy to find in Frontiers. So how does it work? Well, we start with the concept of an address decoder element. And this is basically a feature detector in conventional neural network parlance. Each address decoder element samples a small subset of the input data, and this is a bit like a synaptic cluster. So if you imagine we have, now this is doing the Microsoft thing, all right? So it's the image is showing is not the one I expected to appear here. This one was deleted a long time ago. But anyway, it serves the purpose. If you look at biological neurons, then the inputs to a biological neuron are tree-like structures called dendrites. And there's growing interest in the fact that what happens on a dendrite is local nonlinear computation. So the standard simplified model of a neuron is that all the inputs come in, they're multiplied by individual weights and then summed and all accumulated in one place. Biological neurons are, of course, far more complex. And in those input processes, local nonlinearities are having a significant effect. So effectively, you've got feature recognition going on in perhaps hundreds or thousands of places on different branches of dendrites on the input to an individual neuron. So the neuron is doing much more than just accumulating all its inputs. So we think of these address decoder elements as being a bit like a section of a dendritic branch. So here's an example, and I'm going to use the familiar MNIST data set as an illustration through some of this. So this picture is showing an MNIST handwritten digit 8, and a particular address decoder element is sampling a subset of the pixels. Here it's shown sampling 6 of them. We typically normally cluster these a bit more closely than this shows, but in principle it can be random. And each of those pixels has associated with it some kind of weighting, which can be simple integer weights. And then they are added together and used to compare against the threshold. And when the weighted sum of the connected input values reaches a threshold, then that address decoder element fires, or it's active, however you want to think about it. So this looked like a very conventional, simple neural model, but we think of it more as the process happening on an individual dendritic branch of a neuron rather than the function of a whole neuron. One of the key things here is that when we generate these address decoder elements, which essentially we do randomly with some clustering, we then learn the threshold at which this address decoder element fires using a homeostatic algorithm. So we basically adjust the threshold until each address decoder element fires at the same rate. So each ADE may fire for roughly 1% of the input samples in the training set. Then, if we take those address decoder elements, we form address decoders, which are banks of address decoder elements. And the simplest way we think about this is in accessing a two-dimensional sparse binary coincidence memory. We have played with higher dimensional memories. So the 2D memory looks at two-way coincidences, the 3D memory, three-way, and so on. And it can be much more random than this, but the square or approximately square SBC memory is the simplest way to understand it. So here we've got one address decoder running vertically, one running horizontally. Each of those has, say, 1,024 ADEs in it. And the inputs are presented to those ADEs. A small subset of each of the ADEs in each address decoder is active. And so you can imagine that we have a small subset of the rows active and a small subset of the columns. And where an active row meets an active column, then we have a memory position that itself is activated by this process. So effectively, as I say, each ADE can be thought of as a feature detector, and the active memory elements correspond to feature coincidences between elements in each of the two address decoders. It's sparse. We typically operate in the region of 1% activity in each of the address decoders. And that means that in terms of the number of active memory locations, then it's sparse squared, if you like. If 1% of the rows and 1% of the columns are active, then it's 0.01% of the memory locations are activated for any particular input. And when that memory location is active, then it performs a function. The function depends whether we're training the memory or classifying with the memory. But basically, this activation process that's illustrated here is the same for both operations. Now, if we look at a particular column, we see a number of memory locations activated in that column, and then we take a cut across that column, and what we see is that at each of those memory locations, we have a number of bits of memory, and for MNIST, where there are 10 classes, if we use one hot coding, then we'd have 10 bits of memory in each of those memory locations. So the other encodings are possible, but one hot is the simplest. So if you imagine that a number of previous operations have set a number of locations in the memory, those are indicated by the gold color here. And we're now training with a new data item, which corresponds to the digit 6. So this is supervised learning. Then what we do when we train the memory is we set bit number 6 in the active memory locations. And that's a simple single pass operation. Obviously, if we expose the data, expose the memory to the same training data item again, we get exactly the same ADEs active. We get exactly the same memory locations active. So we'd be setting exactly the same locations again. In other words, that would make no difference. So multiple passes through the data in the absence of training noise makes no difference. The memory learns everything there is to learn in a single pass. And the input here is from class 6, so we set those number 6 bits. And in the training or the writing phase, then that's all we do. Those bits are set, and they may already have been set by other operations. They may not. It doesn't matter. We simply set them irrespective of their previous value. And then when we're doing inference and reading from the SPC, all we do is activate the memory in the same way, but now we just count the number of bits that are set across the memory for each class. And the inferred class is the class with the highest count across the whole memory. Okay, so that's very simple binary operations throughout. No floating point arithmetic is required. It's all simple fixed point arithmetic. And of course, if the classes are not coded as one hot, then the inference process has to make some different assessment of the class bit counts, but we'll stick with the simple example here. And so just doing that, what do we get? So I've mentioned MNIST already, and here we see the basic results from MNIST. Now MNIST is a nice example. It has 10 classes, they're balanced, which means that the number of training examples is the same for each of the classes. So you get a balanced set of training. And here we're using address decoders with 2000 ADEs in each dimension. And we combine various different address decoders through a number of sparse binary coincidence memories. And those are detailed here. But the performance is shown by the graph on the right. And what you can see is that we're getting around 95% accuracy, which, as I said earlier, is not state of the art on MNIST, but it's a reasonable performance. But what's interesting about this is the nature of these graphs. Now, it's not perhaps obvious, but what these graphs are showing is how the inference accuracy is affected by noise. And that noise may be added during training or during inference. And the different colored lines on this graph each represent a different training noise. So the yellow curve was trained without noise, and then the noise goes up, and this is Gaussian noise, and the standard deviation of the Gaussian noise, I think, goes up. I can't actually read the thing in front of me because it's too small, but it's 20, 40, 60, 80%, and so on, Gaussian noise. So quite high noise levels. And the curve, the black curve at the bottom, is the one that was trained with the highest noise level. And what you see is, well, the black and blue curves, when the test noise is high, the models trained with the highest training noise perform best. So their inference performance under zero noise gets slightly worse if they're trained with significant noise levels. But their inference performance under noisy inputs is significantly better if they're trained with noisy inputs. That graph can be viewed in 3 dimensions. I'm not sure if that makes anything much clearer, but what it shows is that over quite a high region of test and training noise, the performance of the system is sustained. Now, if we compare that with one of the older artificial nets that was used in the early days of MNIST, and that's LeNet 5, which is quite a respectable network. And this is trained over 100 epochs with various parameters that I don't necessarily understand, early stopping and static noise. Then what you see is that the performance of that artificial net, which starts very high at the left of the graph, in particular when it's trained with zero noise, then it gets slightly better performance than the BitBrain model. But remember, this has been exposed to the data 100 times to get to this performance, whereas the BitBrain has learned it in a single pass. And what you see is when you add noise, the performance drops very markedly. So we can look at those two performances together and compare them with BitBrain at the top and the Net5 at the bottom. And what you can see is quite different characteristic behavior. Okay. Basically, Linnet collapses under noise and BitBrain doesn't, is the simple conclusion then. Now, Linnet, as I say, is a fairly old network. If you take a state-of-the-art artificial net and do the same comparison, the state-of-the-art net here is CapsNet. Again, CapsNet performs much better than the Net5 under noise, but it still doesn't hold its performance up as well as BitBrain under noisy inputs. So we think we have something interesting here, and using feature coincidence detection appears to be a rather robust way of performing classification. Now, MNIST is a relatively simple test. We can obviously apply the same principles to other data sets. One we've looked at is EMNIST, which has gone from 10 to 62 classes. It's unbalanced, so there aren't the same number of training examples for each of the classes. The overall setup, hello.
Can you go to the previous slide? Is it okay to interrupt you with questions?
Yes, up to a point.
I want to make sure I understand how it works. So essentially, if you have a noise of 100, it means that the signal completely disappears. I mean, maybe I misunderstand something. You are learning the signal which is literally absent. With accuracy of 100.
It's not 100%. It's an 8-bit value. So the range of the signal value is 0 to 256. And the noise here has a standard deviation of 100 in 256. So the signal to noise ratio is about 2 to 1, I would guess, in this one. So the signal hasn't completely vanished. Okay, does that make sense? Yes, yes. So EMNIST is a harder problem, and anybody who's looked at EMNIST will know that there's some fairly obvious class A aliasing. So little o, big O, and 0, when handwritten, are quite difficult to tell apart. Likewise, L's and 1's and S's and 5's and so on. So it's a much harder problem, and that's the BitBrain performance on EMNIST. But again, if you compare it with the Net5 under noise, then it holds its inference accuracy up much better than a conventional artificial net, and that's Linnet, which is one of the older ones, or CapsNet, which is one of the best networks in this area. Again, you can see that the noise performance is different, and particularly under significant input noise, the noise performance is quite a lot better with BitBrain. Again, I remind you that BitBrain has deployed single pass learning on this data set because multiple passes make no difference. The artificial nets have been trained over 100 epochs on the test data. Another valid comparison is to look at other single pass methods. And here, this graph is comparing BitBrain, which is the green bar on the left, with CNNs trained for only one epoch. Of course, they're not designed to be trained for just one epoch, so it's not surprising that performance is low. Those are the red bars. The blue bars are other algorithms specifically designed for single pass learning, and it can be seen that BitBrain is slightly higher performance than the best of those. So it's competitive with the best of the single pass learning algorithms, and that's fairly encouraging. Now, the next slide is a video which is going to demonstrate the Raspberry Pi implementation being used to do MNIST inference. there is a histogram that will appear on the Raspberry Pi screen, and the histogram represents the 10 classes of digits from left to right. You have to watch fairly carefully to see. Oh, the video works. That's a surprise. So there's the sound on this video is not really particularly useful. Just another noise source. Okay, so you saw 3 different digits being entered just by using a touch screen. And if you look at the histogram, you can probably just about make out that in each case, the tallest bar was the correct inference for that particular handwritten input. So it's been trained on the standard MNIST data set. It's being tested just by physically hand-entered digit. And it's working pretty well. You'll also see that each of the classes has a particular bar. So you can also infer something about the confidence of the network from the heights of the other bars. So if the highest bar is very little higher than the second highest bar, then you know the network's less certain that it's got the class right than if you see a strong difference as you see here. Now the next, I've got another video coming up, and the next one is showing an example of single pass learning. Again, I should explain that the network has been trained on MNIST, and it's given a new character, which is a right arrow that doesn't look particularly like any MNIST digit. But if you ask it to make the inference, it will come up with an answer of some sort. But if you then add that right arrow to the set of classes by defining a new class for that, then you'll see with just a single example, it then recognizes the second hand-entered right arrow. So there's a right arrow. What does it look like? Well, it looks like a 5. I'm not really sure it does. We'll make a new class. I think it's class 13, if I remember right. We train it, put in another right arrow, hand-entered. This takes a little time because the network is absorbing the data, but you can then see the new class on the right is strongly dominant. So with a single training example, the network is recognizing a hand-entered right arrow as being more like the previous right arrow it's seen in terms of feature coincidences than it is like any of the other classes that the network was previously trained on. So that's quite nice. The other feature in this picture at the front, which isn't being used in the 2 videos I've just shown you, is a small Spinnaker board, but we'll come to that later. What else can it do? Can it do anything slightly more useful than MNIST? Well, one area we've explored a bit is using BitBrain to classify EMG data. And this slide shows EMG data being taken from human subjects with 12 channels, and a subset of the data was taken from the able-bodied individuals who provided the data. And for this, there are quite a lot of possible tasks of which we use subsets to see how the classification works. I think if you want background to this EMG data set, then the paper mentioned at the bottom of this slide describes what's going on here and quite a lot else. The kind of things that we're looking for are inferring gestures, and you probably can't read what's on this slide, but you can see the top line are just various different hand configurations with different numbers of fingers or a clenched fist. And the second line are movements, so that the hand is moving one way or another in particular configurations. And the bottom two lines are a whole set of different hand functions, grasps, and that kind of thing. Not quite sure how to describe them. And what that data looks like is we take the EMG samples over a particular period of time, and the 12 channels represent the vertical axis on these pictures, and the horizontal axis is effectively time, and it's showing the signal strength on the individual 12 channels as a function of time. So you can see that for the bottom, the top picture here is one particular task, and the lower picture is a different task. You can view this effectively as looking at images, so it's very like image classification in the way that this process works, as is a lot of time series analysis by artificial nets is done by effectively casting the time series into an image-like format and then using image analysis type algorithms. And so we've got 512 samples of the EMG readings, and these are turned into frames. And the signal energy is taken in logarithmic form, normalized in the 0 to 255 range. So it's basically 8-bit integer data. And it's a balanced task distribution. The data sets are divided 90-10 into training and test data for evaluation purposes. And again, because we're interested in the robustness against noise, this is what noise looks like as it's added in the tests that follow. So the original data set is shown on the left here, and we use two different forms of noise. The Gaussian noise with two different standard deviations is shown at the top on the right. And again, the standard deviation here is integer numeric. So we're on the scale 0 to 255. So the standard deviation of 20, that's order 10% of the signal level, and 40 is 20%. And the other sort of noise we use is salt and pepper noise, where individual pixels in the image are turned to effectively zero, black or white, with a certain probability. And so you get a feeling for how much corruption the noise represents added to the data. And when these experiments were run, again, the graphs are organized in a similar way to the MNIST data. What you can see is with increasing test noise, you get somewhat reduced performance, but actually the performance holds up very well. And the general performance level here is comparable with, or if not better than, conventional classification algorithms that are used on these data sets. This one's classifying the images shown at the bottom of the slide. So there are 8-9 different samples, different possibilities here. So the baseline of these graphs represents random chance. And you can see that the results are a long way above random in both these cases. And the second experiment was with a smaller set of 4 different grasps. And again, you can see the classification holds up very well under noise. Again, the bottom of the graph is now 25% and 1 in 4 chance of getting it right randomly. So these look like quite useful results and quite competitive with systems that are currently used for these purposes. It's fairly early days for working with this data, but very quickly we've got results which look competitive with established methods for solving these problems. So I said I'd mention Spinnaker. I guess most people have some idea what Spinnaker is about, but for the last 20 years we've been this machine with 1 million ARM processors, primarily aimed at brain modeling applications. Even with 1 million processors, you get nowhere near the scale of the human brain, but somewhere approaching the scale of a mouse brain. And we've used this machine for all sorts of brain modeling applications. The machines we built, the work started with the design of the silicon chip, which contains 18 cores, and we can put those chips on a board with nearly 1,000 cores per printed circuit board, and then we can assemble large machines with that board. And the 1 million core machine at Manchester has been running an open service under the auspices of the EU Human Brain Project at half scale since the end of March 2016, and at full scale since November 2018, with lots of external users. But that's background. What we did here was a distributed implementation of BitBrain on Spinnaker using the parallelism of the machine and effectively allocating processor cores to small groups of ADEs within an address decoder and small subsets of the SBC memory, and trying to get the distribution to optimize the parallelism of the implementation. So the example implementation that we put together used 32 cores for the address decoder elements and 384 cores for the sparse binary coincidence memory. And then we can feed the same data sets through and see how they work. And here, the Spinnaker board at the bottom is actually doing the work on this occasion. So you see the finger is pushing a different button. It's using the Spinnaker based algorithm for predicting the results. And since it's a relatively straightforward binary algorithm, of course, it performs pretty much identically to the Raspberry Pi native algorithm. So I think we're a little over time, but yeah. I'm about to conclude anyway, so we'll bring you back towards the original schedule. So what I presented is BitBrain, which is a novel single-pass learning mechanism, which looks to work quite well. It gives accurate inference, not state-of-the-art by deep network references, but certainly best in the single-pass class, and pretty good compared with state-of-the-art networks, but very good robustness to imperfect inputs. It's very simple. Once you've got the concept, there's nothing complicated going on by way of floating point or error back propagation. It's just simply setting bits in a memory and then counting bits. It can learn continuously, as the videos demonstrated, and with single pass. And to give you some idea of the performance, I did a software implementation of BitBrain on my MacBook Air, which is a 3.2 gigahertz Apple M1, and using just one of the 8 cores on that machine. And that does the 10K inferences for the MNIST test set in just under half a second. So it's pretty quick processing. And it can be implemented on relatively small systems. It has a reasonable memory requirement, but not excessive. And we've already been playing with some improvements. So if you do a bit of data augmentation, you can get improvements in performance. And when the training set isn't balanced, doing some weighting of counts also gives you a bit of improvement. But we have a lot more to do. It's early days, and here are just some of the things that we want to do. And if you want to know more about Spinnaker, we put out an open access book. So it's free to download in its PDF form from the publisher's database. And that describes the 20 years of the project and a bit about what's happening next with Spinnaker 2. So thank you for your attention. And with that, I'll stop.
Steve. sorry that we don't have that much time because we're pressed with the following session. But 2 questions I will sample. There is pause.
Sparse question sampling. Yes, very good. There's one.
Alex.
I think the question is about continuous learning with more than one pattern. I mean, I demonstrated learning one new pattern. Yes, I think you can add more classes, and if you think about it, each class with one training example is adding very few bits to the memory, so it's making very little difference. The SBC memory has the usual characteristic of binary memories of this nature, that its information content is maximized when half the bits are set, and if your training process results in more than half the bits being set, roughly speaking, the performance will then start to decline, and that's very standard for these kind of memories. So it pays to keep the memory occupancy below 50%, but if you're doing continuous learning, then quite low. Yeah.
Jordan.
Okay, so just on the demonstration where you drew the right-facing arrow on the MNIST data set, it looked like the algorithm actually gave a class confidence for each class. So I was just interested in whether you investigated novelty detection to determine whether the actual pattern that you'd input didn't belong to any of the classes that it's seen.
Yeah, I think that's quite an important question. The direct answer to your question is no, we didn't investigate that. But is that an important thing to investigate? Then yes. Obviously, if you can see that inputs that match classes that have been trained on score much higher counts than inputs that don't match any of the trained classes, then the memory should be capable of producing a don't know response, which would be a good thing. Yeah, but we haven't investigated that in detail, but it's an obvious, important thing to look at.
Okay, thank you.
Excellent question. Yeah, thank you. Okay, so Steve will be here obviously today and for the social.
Yes.
So keep asking questions whenever you catch the sight of Steve or he catches the sight of you.
All right.
Thank you very much.
Thank you. I assume somebody knows how to drive this.
Yes. I think Anatoly is now going to chair the next session. I'll be back.
Thank you. Thank you. Thank you, Steve.
PDF file.
Do something like
This
screen.
I think this
Full screen.
Yes. I think they have sent it in. No.
It's paper, but there is no Adobe here. It will open here. So let me do it in the following ways. F11, where is that F11? Screen. Can you ask the guy to basically about?
Just get done with this.
Which this?
We have the option.
There's a full screen mode, yeah. So,